And what we have found in some of our customers' battery is that about 30% of the cells were faulty before the battery was operational. The point is not to say, let's all of us point fingers at the manufacturers. No, the point is to realize that the battery management system, which is a software provided by the manufacturer, it was never designed to be your commercial brain. That's not its job.
So that gap between reported capacity and real-world performance is where storage returns can quietly unravel. Good morning, good afternoon, or good evening, wherever you are in the world. This is Climate Confident, Stories and Strategies that Cut Emissions, episode 286, and I'm your host, Tom Raftery. My guest today is Ashutosh Vats of 3E, who's working on battery intelligence. We're going to explore why storage profits depend on accurate operational data, not just cheap hardware or clever trading, and why operators need one shared view of what the battery can actually deliver. Let's dive in. Ash, welcome to the podcast. Would you like to introduce yourself?
Thanks, Tom. Thanks for having me. My name is Ash. I started out my journey in India, moved to Germany working on hardwares with EVs, then moved to the US where I was working more on the deep tech side, and now working with 3D where I'm working on batteries. And yeah, it's a very exciting space.
Great. And tell us a little bit about 3E for people who are unfamiliar.
So it's a company based in Belgium, which is a spin out from IMEC, which is a very famous lab. We started back in 1999 as advisors in the renewable energy space. So basically advising across the value chain of a renewable asset from day zero of planning a site to decommissioning when the asset is no longer working. But as the industry was maturing, we realized that there is no way for the industry to scale without adopting digitalization, which is, I think, has been the core of the industry for the last decade. So in 2010, we started working on our digital product, which is called Synaptic, which is an asset performance management solution for power producers and asset owners to proactively manage their sites, run the operations, and optimize their yield for PVs, but for BESS, optimize the capacity that they have and make sure they can get the returns that they wanted to have in their business plan. So that's a bit about the company. We're based out of Belgium. We're 150 people with offices in the US, across Europe, across South America. So yeah, that's a little bit about us.
Okay. And what pulled you specifically into battery storage?
I think if you look at the market, there's a lot of things happening right now, right? I was quite fascinated by the idea of how are we going to achieve flexibility in grids. And I was quite interested in that idea, which actually led me to join renewables in the first place. But having been in the solar for the last couple of years, it was really fascinating to see that there is no way that you're going to find flexibility in the grid without solution like batteries. So I think batteries was a natural solution to the industry where we really wanted to make sure that the generation and the demand on the both sides of the end are managed well. Otherwise, yeah, you can have catastrophes, for example, like in Spain, which happened last year. So yeah, I think it was a natural evolution into the space where the industry was going anyways.
And storage has gone from niche to now, I think, one of the central pillars of modern grids, and it's happened remarkably quickly. What do you think has changed in the last few years that made battery storage strategically indispensable?
I think the first thing that has changed is as an industry, we are out of the LCOE era where we were maximizing the cost of production. And hence the margin was the way to make money from the cost that you put. And I think for the last 10 years, we were obsessed with the idea of how cheap can I build a battery site. But now we have evolved from that. The price of the battery hardware is dropped by 93% in the last decade. The revenue streams are growing like hell, I think, in a lot of markets. So if you look at, for example, Australia right now, 49% of Australian capacity is in queue and it's battery. So it is still in queue to be added to the grid. If you look at Germany, we have the same. It's doubling almost from every quarter. And we are, I think, in two sort of pathways. One is obviously the negative prices that we see across the markets has gone insanely unstable. So in some markets, for example, Germany last year was 571 hours of negative pricing, which is a lot when you think from a power producer mindset. And what that has done is we cannot afford to have just a PV site on a park and think, okay, we're going to manage the electricity that we have generated and the grid will be ready to insert this energy or capacity. And that is never the case. It is never the case that it is so stabilized. So I think that stabilization, the flexibility, the curtailment numbers, the cost of battery in whole, that has led to a point where we are today, where the total capacity of battery that we have installed across the globe has crossed 100 gigawatt. And to keep in mind that the time it has taken for batteries to cross 100 gigawatt, it was 5 times more than it took for solar PV to cross the same. We are at an insane speed, but with the same speed comes responsibility that we need to manage well. Otherwise, we might end up repeating the same solar PV story.
And you mentioned batteries and the revenue people get from batteries or organizations get from batteries. And most people would intuitively think that the revenue from batteries comes from energy arbitrage, take in the energy from photovoltaic or wind when the price is low and then sell it to the grid when the price is high, when there's high demand and not a lot of generation. But that's not the only way batteries make money, right?
No, not really. I think for batteries to make money, there's a lot of ways today in the market. If you really think of batteries, they are a financial asset class. They're not a generation asset class like a solar PV, for example, where your goal is to produce and that's it. So I think we're a moment in the industry where there is so many different markets that have been growing across the different globe, where now we have like completely new ways of selling the energy. So if you think about it, like imagine a 100 megawatt battery that you have installed on a site. Your goal is to stack revenues. Now, what does it mean to stack revenues? It's an industry jargon for something that means a battery can sell multiple things at once. That's it. So it can sell electricity at lunch when the prices are low, for example, and buy it back at dinner because when the prices spike, you can sell it higher. And that's arbitrage, what you mentioned, right? Then it can sell its ability to be available in the market, which is basically capacity markets. It can respond very quickly to the demands, which is the frequency markets. So the dream is you stack all of these and the battery earns from several streams at once. That's where we want to go. But the problem of that is every one of those streams penalizes you when you don't deliver what you promise. So think of it. There are imbalance fees in Germany. There is derating in the UK capacity market. There is loss of availability payments. There's a lot. So if your forecast of what the battery can deliver is wrong by 10%, your downside actually is far worse than 10% because the penalties will stack as well. So yes, you're right. There's a lot of ways to make money, but at the same time, I don't think we have the maturity to understand what is a sellable capacity. I think we are so focused on batteries as a revenue asset that we have completely forgotten that end of the day, it's the hardware that has to produce in order for us to sell. And if you go wrong on that charge and discharge and operational parameters, no matter how much revenue stacking you can do, you cannot because you don't have the capacity to sell. So Indeed, yeah, we have a lot of dynamics that have changed across the market, but at the same time, the end of the story is more dependent on the operational parameters of the battery, which is how you operate the battery.
And that disconnect you referred to about the operational parameters of the battery, you come from, as you mentioned, the EV space. I've got an EV, it's a Kia EV3. Kia tells me it's got an 80 kilowatt hour battery usable, but in fact, when you do a bit of research, they actually put, I think it's an 88 kilowatt hour battery into it. So there's a difference there between what they're telling me and what's actually delivered by the battery. Is it similar? Is that the kind of difference you're talking about between what the OEM says and what's the reality on the ground with the batteries that are delivered?
Yes, exactly. So I think one of the key things that you need to first keep in mind is the battery. Let's focus first on the manufacturers. The manufacturer's job today and I'm not bashing them, but the manufacturer's job in the industry of batteries is to produce and produce really fast right now. Because there is a gold rush era that we are in right now. The rate at which we are commissioning battery sites is insanely high, which is 5 times higher than how solar PV was when it was maturing. And that tells you that the supply chain frameworks that has been put in countries like China or Europe or US, they were actually not ready for this demand, which is why there is a test actually that is called a site acceptance test, which is done on the day zero of a battery before a battery goes live. And what we have found in some of our customers' battery is that about 30% of the cells were faulty before the battery was operational.
Ooh.
So again, the point is not to say, let's all of us point fingers at the manufacturers. No, the point is to realize that the battery management system, which is a software provided by the manufacturer, it was never designed to be your commercial brain. That's not its job. If you have to give a job profile of a battery management system, it is in this order. One, make sure you don't burn the battery. It's a safety tool. You make sure you don't go to the worst catastrophe that can happen. You make every individual cells within the voltage window. That's pretty much the second thing. You make sure you balance the cell when there's a rebalancing required. And you report basic state to whoever is asking. That's it. That's all they were designed to do. So the second thing that you need to keep in mind is that the battery manufacturing systems are essentially an edge device. So coming from the hardware industry, compute power that you get on an edge device is way lower than what, for example, we have the capability to provide to our customers. So that is where we create another level of edge. So that's second point. The third point is the amount of data that we are talking about. When you have an EV charger and you see like, an EV car and you see, okay, 80% nameplate capacity that is left, or you can travel X kilometer, the amount of data is almost like 50 times lower than a big container that is put in a car to manage about 100 megawatt hours. 100 megawatt hour sites generate 100 times more data than a 100 megawatt PV site. And that's a lot for companies like us, for example, who are then running analytics on top of that massive amount of data. So there's two things to that. One is that your VMS was never designed to be your commercial brain. And then the second thing is, now take an example of what is that usable capacity actually means in a big container on a utility scale park. So there's two terms that you really need to keep in mind. One is the state of charge, and second is imbalance. So what is a state of charge? It is basically the full energy content that is currently available. In a battery like a container, there is no fuel gauge kind of thing that can manage what it was in and what was out. So the way that manufacturers do it is they infer to voltage, current, and temperature, and then they have algorithms to deduct what should be the usable capacity. In an LFP battery, which is a lithium ion battery, that number can be off by 15 to 30%. And that's a lot for a battery which is trading and the trading window is millisecond. So at least in my experience, and maybe I'm biased by because I only see the worst cases, but it's very wrong. And the consequences of it is very high, as we were talking, because of penalties and overcommitting to a capacity. The second thing that also happens is there is an imbalance in batteries. So it's a complex system, to be honest. I mean, a lot of cells, you have a lot of electrochemical modeling that is inside, which is, I think, one of the marvelous things that we have came up with as civilizations, to be honest. It's insane that we can store that amount of energy. But inside those cells, so you have 1,000 cells in parallel that are grouped into modules. And then modules are grouped into racks, and then racks are grouped into containers. And that makes a whole system. So the analogy there is they're not identical. So after around what we see is 12 months of operation, the spread between the strongest and the weakest rack can easily be between 9 to 15% difference. What that means is that the system can only operate as well as its weakest rack. So it's a bit like, think of it like a bicycle race where the team has to finish together, but you can sprint as fast as your slowest rider. And if you don't know, this is very important. This is where I think analytics comes in. If you don't know which rider is your slowest, you are underbidding for the whole time. That's really the key metrics that the operators need to get on top of.
So you think the battery industry today is relying too heavily on kind of trust me data from the OEMs?
Imagine you're in a day ahead market and your trader has committed to deliver 50 megawatts during the 7 p.m. peak. At evening, people are at home and the peak is going to be higher. The reality is, let's say that the battery's true deliverable capacity is 42 megawatts and you've committed 50, yeah? Because of imbalance you didn't know about, let's say. So you under deliver by 8 megawatts. That will trigger imbalance settlement if you're in the UK market at the negative price scale of the market, which can be sometimes 5 to 10 times of the spot price. Then you repeat this across 365 days, being 2 to 3 trading windows per day, let's say. That is what 700 to 1,000 imbalance events per year per asset. Now add your availability reporting was wrong because you didn't meet the usable capacity. So you lose the capacity market payments as well. And then obviously, in order to meet all of this, you were like, okay, let's cycle more. So you degraded the battery as well. So in a way, everything that could go wrong went wrong just because you have a black box in front of you that you put your hand and you don't know what's going to come out. As a result, I think 80% of the industry is underutilizing the usable capacity of the battery. And everybody in the boardroom of a power producer turns to a revenue optimizer or a trader saying, hey, why are we not making money? But actually, the person who should be in the driver's seat should be an operator and not the revenue people, because it's one thing to make sure that, okay, you have the 50 megawatts that you wanted to trade, but then the second thing you want to make sure is how many cycles are you going to make? And what is the impact of those cycles on your IRR? Because a battery has a lifetime as well. So you want to make sure you avoid the idea that you have to, I don't know, augment the battery in the middle of the life cycle, which is very costly, to be honest. And that you really need to avoid. And at the same time, what I see in the industry is the way people are avoiding this is by simply oversizing the sites. So they're like, if I can only understand 80% of the battery's capacity, let's oversize by 120, because then I have the 80 that I know, so I can still deliver the 80 because the 20 will anyways be wrong. So that is not the right way to approach the industry.
Surely warranties kick in at some point, though. I mean, if I've bought a 50 megawatt battery from a battery supplier and it's only delivering 42, shouldn't there be some kind of recourse there from the manufacturer?
Yes, you do have the recourse there from the manufacturer, but the problem is, I give you an example of a site that we were just looking at yesterday. It's a site that has been running for 2 years, and the state of health, which is talking about the degradation of the battery, is at 100%, meaning it's completely healthy from the manufacturer. Now, there is a warranty period where the asset owner can go to the manufacturer and say, hey, what you promised was not actually the reality. But the manufacturer is actually not showing you that. So you're like, it's all good, it's 100% state of health. And that is never the case because of many multiple reasons. So, yeah, you have the warranties in place, but the amount of time and effort that an asset manager or technical asset manager or an operator is spending today to manage these warranties, it's about 40% of their time. Whereas they're an asset manager, they should be optimizing the asset and not spending their times on headaches with manufacturer. So there is a massive need of intelligence on that layer, which is really why I think we've worked so hard for the last 4 to 5 years on developing that data layer, which allows you to, one, have the true visibility across your portfolio using a digital twin. So what is a digital twin? I think it's a very known concept in the industry in general, but it's the difference that approach that we have adopted is that it's an electrical, chemical, thermal model that runs with a mathematical model of the cell's electrochemistry. So it takes the same operational data of the BMS or the battery manufacturing system has, which is the voltage, current, temperature, but instead of just reporting it, it is capable of running a continuous simulation of what is happening inside the cell. So the twin that we have built is based on PyBan. It's a Python battery mathematical modeling. It's an open source electrochemical framework that was developed by Oxford with Imperial College in London and Faraday Institution. So very well regarded in the industry. And I think it's a gold standard today in the academia, which is used by the increasingly used by the industry. So the model can decompose degradation into its physical causes. So what caused the degradation? And that's, I would say, if I had to take another analogy, is the difference between having a thermometer and having a doctor, which is you see something is wrong, but you need to know why is it wrong and can you do something about it. And so there's a lot of that usable capacity that is recoverable, that using these insights you can actually work on them and recover them. It's not as easy as it is to recover yield in PD as batteries because it's way more complex, which is why it's even a 1% improve in your usable capacity has a direct impact on your revenue that you will make at the end of the year. So indeed, you're right. There is warranties, but they are typically the single contractual exposure on a storage asset. They are generally millions of euros per site that people are paying. And yet, most monitoring platforms simply provide the BMS reported SOH in the industry today. So it's really hard to have the manufacturer own system and they have the warranty because they can obviously hide what is happening in the platforms.
Okay. A lot of this sounds very lithium ion battery specific, and we know that a lithium ion battery today is a bit like a leased sports car with strict mileage penalties. Operators are terrified of pushing it too hard. But on the other hand, you have what are called flow batteries, and they behave more like industrial machinery, less glamorous, but happy to run continuously 24/7. If flow batteries scale commercially, do some of these utilization and degradation problems become dramatically less severe?
Yes, we cannot say at the moment, to be honest, like precisely if that is going to happen. One of the key differences is it's about the duration of the batteries. So you can be 2 hour, 4 hour, 8 hour. There is even we are talking about 24 hours now. But the point is, as soon as you go beyond 4 hours, I think the LFP lithium ion batteries start to seem less attractive than the flow batteries. That is for sure. So, for example, in Texas, where the 8-hour battery has been deployed a lot, I think the highest, if I'm not wrong, and there, I think there has been some use cases of the flow batteries. But at the same time, it's even harder electrochemical sort of model to deduct with the flow batteries, given what we have in the LFP batteries today. So I think the solution to degrading and making sure we are on the top of this is rather more on the stakeholder collaboration side. If we don't improve that, I don't think technology alone is going to fix it. So if we step back, you take batteries as an example, you have like 3 clocks. You have the first clock, which is an asset owner or a power producer, which is thinking, and their clock speed is monthly, annually. They want to have their annual revenue or the monthly revenue and so on. The language they speak is ROI. They speak IRR, business plans, and so on. And the key question they're thinking is basically, am I hitting my financial model? So that's your asset owner clock. Then you have a technical asset manager clock, which is their clock speed is daily or weekly. They're daily looking at the battery, what's happening, what is the KPIs, and they're all about these KPIs. They're about state of health, state of charge, round trip efficiency, and so on. The question they're asking is the asset performing to the right specification? So these are the guys who really deal with the manufacturer's degradation problems and the tied into batteries and so on. Then you have the third one, which is commercial trader, whose clock is much more granular. It can be sometimes seconds or milliseconds or even minutes. The language they speak is capture prices, it's dispatch optimization, and so on. And the question they're asking is, how much can I sell right now? The problem is the asset owner sees a year, the trader sees a minute, and the asset manager sees a week. And without a shared truth layer, they're three blind men describing the same elephant. That's the problem. So I agree with you that the technological evolution in this space is going really fast, and I'm really happy about that. At the same time, if we do not have conversations on the fundamental problem and the disconnect on one shared truth layer, I think that we will never solve the idea of, hey, did we actually make money from the battery? And did we actually had revenue from our investment? We have today connected about 5 gigawatt hours of battery, in total 50 gigawatt in our platform, but a part of it is solar PV. And the benefit of a tool like Synaptic is not purely to crunch data, put analytics, but it is really to put these three stakeholders with the same source of truth. And so a trader is receiving the API with the state of charge. Asset manager is looking into the system on the KPIs. And then asset owner is using the same data to challenge the manufacturers. But I agree with you to come down to the point of technological evolution. I have really high hopes on the flow batteries. I'm really curious and interested to see its use cases on a utility scale level. So I'm really looking forward to that.
Yeah, me too. And you mentioned ERCOT there, and ERCOT is the Texas grid. I was looking recently at the difference between the Texas grid, ERCOT, and the Californian one, which is operated by CAISO. And California seems to increasingly use batteries for sustained evening discharge. So they've optimized for the longer, roughly 4 hour. I think they've incentivized 4 hour batteries, while ERCOT, despite the 8 hour ones you mentioned, the vast majority of the batteries that I'm aware of in the ERCOT system seem to be more 2 hour rather than 4 or 8 hour. And again, that's just a question of the incentives, I think. Which model do you think, the 2 hour versus the 4 hour greater, which model delivers greater emissions reductions? I'd say would be the first thing I'd want to know. And at what renewable penetration level do grids stop needing fast batteries and start needing deeper batteries?
That's a very good question. I would try to step back a little bit and give a bit more broader perspective before I answer it. So there's a lot happening in the market in terms of maturity of revenue streams. I think there are some markets that we will look back in the future and be like, okay, these markets have paved the path for us to really monetize an asset class like battery, coming on the duration of the batteries. So I think Netherlands was a great example, which has been now the nameplate example of Texas and ERCOT as well. The Dutch market was restructuring around 4 hour systems. So they said 2 hours is not good. And the developers were explicitly pivoting away from 2 hours to 4 hours. Why? Couple of reasons. First, the FCR, the frequency response, frequency reserves, and the AFRR markets, they saturated. The wholesale arbitrage requires more energy capacity to capture the full spread. So when you said the depth of the battery's capacity starts to matter more because the wholesale becomes bigger. The corporate PPAs and the capacity market participation rewards also longer duration. So there is been a shift in the industry. If you take Europe, for example, there was a 2026 Energy Act that is structurally pushing this. So the same shift is happening in Italy, it's happening in the UK, and it's happening in Texas as well, where the duration is migrating from 2 to 4 hours, even to 6+ hours in some markets. That is one answer on the markets. A lot of markets also are seeing a saturation of ancillary services where the wholesale markets are starting to again become bigger. So that's one. Then on the same topic, there's a lot more interesting things happening across the globe as well. So Germany is a great example as well. Germany has took their 4 TSOs, which is basically the grid operators, in January of 2026, and they launched the first ever market in the world that is called grid inertia. And what they wanted to do was it's a way to have a long-term fixed price contract for 2 to 10 years on a premium product with a 90% availability. And that would change the entire game because it transforms a battery from a spot market asset into a quasi infrastructure asset. And that changes the game. So you see, once that's going to happen, we are even going to try to go to longer and longer duration of batteries. And so that we already see we are on that trajectory and it's going to happen. UK also had the same with Stability Pathfinder, which was the name of the policy. Australia is following on the same route. So basically, inertia is becoming a big topic across the globe. Then you have moved from 2 to 4 hours. So those are two examples. And the third example, if anybody is really interested in revenue streams, a market that you really need to follow is Australia. It's the most aggressive, best deployment market by penetration. They have connected 5 gigawatt at the end of 2025, which was 2 gigawatt a year prior. 10 gigawatt is expected operational by mid 2026. The connection pipeline is about 30 to 32 gigawatt, so it's massive. The fun part is that 70% of Australians' grid is grid forming inverters, meaning they also support long duration. And the lessons that will come out of it, we don't know yet, but that will come out of it about market design, about dispatch optimization, about revenue cannibalization, is going to define the playbook for everybody else. So the long answer to that question is we should really look at the UK, Germany, Texas, the Netherlands, Dutch market, and Australian markets, because these markets are really right now paving the path on each individual topic, some on market design, some on dispatch, some on revenue, some on other topics. And that's a reason why I think one of the reasons I believe is that as an asset operator and a power producer, you need to really think beyond the batteries as just storage assets and as a financial tool, because every battery gets essentially built against a financial model, right? The model assumes a certain availability, a certain degradation pattern, a certain revenue mix, and the investment decision happens once, but you operate the battery for 15 to 20 years. And it's funny to me to think that people think that everything outside of those 20 years matters more than those 20 years. And to me, that's a completely the shift of mindset that the industry really needs. We do see that shift with a lot of our customers who want to be the next generation of power producers. And the next generation of power producers are not going to be power producers who optimize cost. They're going to be power producers who optimize revenue, but they do that on a portfolio level. So the idea of revenue streams is really fascinating. And I think, again, going back to thinking like a power producers, make sure you optimize those 20 years that you have.
And looking forward to that, do you think that storage will eventually become the central coordinating layer of the electricity system?
It has to. I mean, there is no other means that we see at the moment. I mean, it should. It should. It already is in so many markets. Like you take examples of we're talking about energy, but at the same time, we also have another boom happening in the industry, which is around AI, right? And that boom is not possible if we do not work towards the battery. It's just not possible because the peaks of the ups and the highs of the depth of charge and discharge that is required by a data center that is training AI model is the difference is about 15 megawatts. And the peak of normal cloud application is about 2 megawatts. So I think it's a must with where we are going with technology, with the solutions we are providing, with the fluctuations in climates accordingly to the needs of electricity and the demand and generation. I think it's an obvious choice.
If listeners want to deploy or manage storage more intelligently now, where should they start?
I think if I can answer your 4 steps to that. The first step is you need to make sure you have a hardware agnostic layer to begin with that harmonizes all your data. So first, make sure you get that right. So you have a tool that doesn't lock you in into different vendors or providers of battery. Because let's say you have SunGrow, let's say you have Captain, let's say you have BYD, and then you have 3 different forums to do your thing. You want to make sure that you have organized data information model. Then second, you need to make sure you have a simulation model running that is based on R&D, that is based on actual effort and understanding of renewables. There, I would insert the line of why I really work at 3D, which is that it's a renewable company that got into IT and not an IT company that got into renewables. And I think in batteries, that makes all the difference. So the second layer is don't take the nameplate of digital twin in the industry as, whoa, this is great. Be a skeptic on that, challenge the providers that you're working with. The third layer is I think we are a bit too blind by the idea of data, and we think data is good, so let's have a lot, and let's have a lot of insights. Let's have a dashboard filled with KPIs and KPIs. I don't think that is a winning approach. The winning approach is not an approach of a cognitive overload for an asset manager. The winning approach is an approach where the system is intelligent enough to guide you and to help you use the expertise that the system can provide to fulfill the needs in your teams. And so thinking that if you only deploy a pure play analytics, you're good, I don't really think so. You rather need to set up a control room operations. You need to set up your network's operations center that can scale over time because the battery capacity that is coming in your pipeline is massive. So you really need to keep that in mind. And the fourth and the most important layer is I see that the world in renewables is filled with digital tools, to be honest. There's a lot of small verticals that we have. And I think the winning playbook is to have a tool which can provide you API-based structuring. So it is open by design, and you can connect different tools to it. So it doesn't become a locked-in system or one thing that you cannot communicate to other things. And I think that's really, really important. So those four things would be the key things that you should look for. And obviously, those are key things that we believe in at 3E, and that's how we've built Synaptic.
Time now, Ash, for the lightning round. So I'm going to give you 4 or 5 quick questions, one sentence answers. Okay, first one. What's the bigger risk, cheap batteries or inaccurate data?
Inaccurate data, 100%.
What's one battery myth you'd kill immediately?
20 years of operation is less important than the revenue.
All right. What's the best storage market today?
UK.
What's the most overrated battery metric?
Ooh, that's a very good one. Most overrated battery metric. I would say round trip efficiency.
Okay. And finally, will software firms capture more value than OEMs?
A short answer, yes. A lot, yes. It's a market of, by 2033, it's going to be a market of 5 billion.
Okay, very good. A left field question for you now, Ash. If you could have any person or character, alive or dead, real or fictional, as a champion for battery intelligence, who would it be and why?
That's a very nice question. Big fan of physics in general. I think the fact that we are using the pi-band model, which is also coming from Faraday Institution, I would pick Faraday with the work that has been done in the past. And I think I really resonate with his philosophies in general. So I think I would have picked that. But in today's generation, if I had to pick to promote batteries, I would rather pick something fun, because I also think it's an industry where we need to have little bit more fun than how we make it today. So yeah, that's a long answer. That was a very good question, by the way.
Thank you. We're coming towards the end of the podcast now, Ash. Is there any question I haven't asked that you wish I did, or any aspect of this we haven't covered that you think it's important for people to be aware of?
No, I think the only thing that I would add is, as much as we have talked about technology, I think it is also an industry about humans. And I deal with asset managers and operators a lot every day. Those are the people I talk with. And I think let's not forget the people who are actually behind these big power plants and so on, and actually running them, understanding these things. So I would say I would send a big round of applause for people who are actually behind these systems and running it, no matter with not enough tools or not enough capabilities and with insane amount of data. But to be honest, it's a commendable job to do. So a big shout out to the guys.
And Ash, if people would like to know more about yourself or any of the things we talked about on the podcast today, where would you have me direct them?
On my LinkedIn or company page or website is 3e.eu, so you can reach out there and you will find contact information, or you can reach out to me on LinkedIn or anyone from 3e on LinkedIn, and I'm sure we'll be happy to help.
Fantastic. Ash, that's been really interesting. Thanks a million for coming on the podcast today.
Thank you so much, John. Thank you for having me. It was really fun.